Hello. I don't even know asynchronous what week. I don't know. I've lost track. I think it's 15. I'm going to today talk about, we're really going to focus on talking about polar equations and graphing them and then using our calculators to graph them. And then we're going to talk a little bit about finding equations of tangent lines to polar graphs and a little bit about arc length. There's not a whole ton we can do here by hand, just due to the nature of the type of work that has to be done integration wise for arc length. But we'll get into that a little bit. Like I said, I really want to focus on polar graphs today. I don't want to make this lecture too long just because I know you've had a lot of asynchronous work the last 2 weeks. Like this entire chapter has been asynchronous. So I don't want to get too crazy, but certainly we can finish out 9.4 and then kind of do a rundown of 9.5. 9.5 is kind of a weird section. There's like a lot in it, but there isn't a lot to do in it. It's kind of just like it covers a lot of topics, but there isn't a lot of work that can be done. So if that makes any sense. All right, let's finish out 9.4. So we started talking about 9.4 last time. We covered over half of it where I introduced you to polar coordinates. Get you guys focused here. Focus. So last time we left off talking about converting between rectangular and polar coordinates. So now we're going to do something similar, except we're going to be talking about equations instead of coordinates. We're going to be using the same formulas that we used before. So I'm going to start out here with example 3. And we'll start out first by converting from rectangular to polar. So we're going to convert the equation from rectangular to polar form. And then, sure, we could say n graph. Sure, why not? So it's a good idea. I really want us to start being able to connect the type of equation that you're seeing with the type of graph you can expect to see. So for A, we're going to have, I'll give you this rectangular equation, negative x plus 4y minus 3 equals 0. Now, this is the kind of equation that you would normally see written in either slope intercept form or standard form. You don't usually see this in what we usually refer to as general form, where you have it set equal to 0, unless it's quadratic, which this is not. It's linear because it has an x and a y, each to the first power. So if we were going to graph this, well, I'll show you how to convert it to polar, and then we'll kind of talk about which way we want to use to graph it. But all right, so we know that x equals r cosine theta and y equals r sine theta. So what we're going to do is everywhere we see x and everywhere we see y, we're going to make these substitutions because we want our equation to be written in terms of r and theta. So we're going to take negative, and then x is r cosine theta. Now, technically, you don't need these parentheses. I tend to show it just when it's a negative and I'm substituting it in, but they're non-essential. And then y is r sine theta. So we have 4 times r sine theta minus 3 is equal to 0. Now, we're not always going to get these exactly in the form we like. I mean, technically, at this point, it's been converted. Normally, we try to solve for r if we can. The reason we do that is because when we're graphing these in our calculators, and I'm going to show you how to do that in a minute, our calculators in polar mode are going to be expecting the form r equals. Very similar to how when you're in function mode, you go to the y equals menu. A lot of times I don't even say go to your graphing portion of your calculator. I usually just say go to your y equals menu. With polar form, it's an r equals. So if we can get this solved for r, it's very similar to what we would do with a function solving it for y. Normally just with a polar graph we solve for r. So we're going to get the r's together, and then anything that's not an r we're going to put on the other side. If you want, I know I've made this more complicated by including those parentheses now. But you can just go ahead and move that 3 over to the other side by adding it to both sides of the equation. And then since we're trying to get r by itself, I know you guys have done a lot of work with this, not with r's, but with y's. We can just go ahead and factor it out, and then we'll just divide out everything that's not in that factor. So go ahead and take out the r, factor it out, and then I'm going to write this as subtraction instead of addition. So this will be 4 sine theta minus cosine theta. And then to solve for r, we'll have r equals 3 divided by 4 sine theta minus cosine theta. So what's interesting is we ended up taking this equation that before you would have had no problem graphing and turning it into this really foreign object where you're just like, what is this? I don't even know what's happening. But let's go ahead, since I asked you to graph it, I'm going to show you how we would graph the rectangular one, as you know, and then we'll match that up to what you're seeing in your graphing calculator with the r function, or the polar equation, r equals. So normally you would see this, you'd have 4y equals, we'll add the x and the 3 to both sides. Usually we have y equals mx plus b, so I'll go 4y equals x plus 3. And then y equals, well, we'll divide both terms by 4. We'll have y equals 1/4 x plus 3/4. So this would be the rectangular in slope intercept form. There we go. So if I was going to graph that, I know that I have a y-intercept at 3/4. Because I know I have a slope of 1/4, so I know I'm going to want to go up 1 and over 4. So let's see, maybe I'll call this 1. Maybe 1, 2, 3, 4, 5. 1, 2. Y, x. Okay, so y equals 1/4 x plus 3/4. So the y-intercept is 3/4. So I'm going to go approximately up here, and then I'm going to go up 1, right 4 to get me approximately right there. And you could, of course, get another point by going down the opposite direction. But it's a line, so all you need to graph it is just 2 points. And that's what it would look like. Now we can talk about how to graph this in our graphing calculators. So over to your mode. I'm already in polar mode just because I was working in polar mode earlier today as I was prepping your lesson. But you need to be in polar. You're probably in parametric now from last week, but get yourself into polar. And then when you hit your y equals, you will get an r. Now I have mine set up for this little circle, which I like when I'm graphing because it really helps me to see kind of where the graph starts and where it stops or how many times. You'll be surprised what happens with these polar graphs. Sometimes they graph over themselves multiple times. So it's really helpful to know how many times it's looped around, and you'll be able to see that when you have this selected. So I showed you how to do that with parametrics, but if you want, go ahead, feel free to switch this over to that line style. Okay. All right, now, when we are graphing the polar form, we have rewritten this as 3 divided by, and then in parentheses, 4 sine theta. Now, just like with parametrics, if you hit the variable button here when you're in polar mode, it's going to give you theta. It's not going to give you x. It's not going to give you t. But if you're in polar mode, you're going to get theta automatically. Just make sure you close off that parenthesis because it's sine theta, and then minus cosine theta. And then close off your parenthesis again to close out your denominator. So let's see what happens when we graph this, because you might end up seeing that you're going to have to switch out your angle theta. So let's look what happens. But you know what you're expecting to see. I can see this. So let's hit graph. Oh, it's so interesting, isn't it? Notice that because I put that little ticker on there, you could kind of see what was happening. It's dark because it's going to get. But it looked like it went whoop, whoop, and it's kind of graphing it over itself. And that all depends on the values that you put in for your angles. So if you go to your window, very similar to what we did for the parametrics, you can always change your thetas. I was at a theta min of 0 and a theta max of 2 pi, but you can make that as big or small as you'd like. Maybe I want to say negative 2 pi even, just to see what happens, and then keep your theta max at positive 2 pi, see if that affects your graph. You can sort of play around with this. It's all new to you. And you can see it just kind of runs its way back and forth. So, oh, and by the way, if you want to, your theta step is basically just how many times it's going to compute your theta in between there. So you can play around with that also. But you can see, though, that this graph matches the one that we have for our rectangular equation that we graphed down here. So I know it seems odd, but technically you can take your polar graph, and we're going to be doing this in 9.5. You can take this polar equation and you can just let theta take on different values and then get different values for r. And remember, r is just the radius, so it's not the same as like a y equals, and we'll look at this later. R is just going to be, you know, if you're looking at this theta angle, like for instance, as this angle goes up, r would be decreasing. So kind of thinking about this angle, and then you would be at this point right here. Get my pencil. So whatever value I would have to be at. Oh, and by the way, if I was at a smaller angle, notice that I would at some point never be able to intersect this. So I only intersect this for certain angles. So that's why maybe starting this at negative 2 pi wasn't really going to change anything for us. But as you start this here at this angle, and then you continue to go upward, notice that the radius is actually decreasing. So your angle is going up, but the value of r is going down, because r is just the distance between the origin and wherever this point is. So there's obviously the distance between the origin and this point is much greater than the distance between the origin and that point. This is what is represented by r. So you might find that if you actually extend your angle beyond where you think it needs to go, you might even see something else happening with your graph. So we have this right now, but let's say instead of going from negative 2 pi to 2 pi, maybe you increase that. I mean, maybe even take it up to 10 instead of 6.28, and then see how that affects your graph. So you can kind of play around with that and see what happens. But again, you're going to get to this point, though, where if once you get back down to another angle, you're going to be parallel, and you're never going to intersect. So you're going to only have certain values for which you're going to be able to obtain points, which is why your graph is going to cut off approximately here, which is what you're seeing on the graph. Once you get below that, you don't have any points that are going to intersect there. Oh, but you would have them recreated over here, which is why you're seeing the zoop, zoop, zoop. So imagine now your angle's up here at pi over 2. Well, now your angle's increasing from pi over 2 to pi. Well, the radius is also increasing because the distance here is less than the distance here. And then you continue to head down past pi. Well, and at some point, you're going to pick an angle theta at which you're parallel, and you're never going to intersect. And you cannot create any more points on that line. But if you keep increasing your angle theta past 2 pi, you're going to start to generate those values over again. It's going to kind of do its thing. So interesting. I recommend just kind of playing around with that a little bit and just seeing what kind of observations you can make between what you know about polar coordinates and what you know about rectangular, kind of putting them together. And just really, I think the most important thing here is understanding just the way this is graphed and the relationship between the value theta and the radius, and just kind of understanding kind of, I always think about these as like sweeping through these angles and then what's happening to the value of r as you sweep your way through. You know, it's kind of hard. It's hard to show this at all, but this is kind of what I do. I sweep through and I just kind of see what happens to the value of r as I do my sweep. Now, we can talk about it more in the office hour if you're just like, maybe I get it, not quite sure. Okay, let's do another one of these. So this is actually a little bit of a more common one that you're going to see when it comes to polars. So the rectangular form is x squared plus y minus 3 squared equals 9. We're going to go through here. And again, we're going to make these substitutions so that we can rewrite this using r and theta. So we know that x equals r cosine theta. Everywhere we see x, we're going to replace it with r cosine theta. And in this case, it's being squared. And then y is r sine theta. So we're going to go ahead and replace that quantity. What you might want to do first, though, since you're going to need to get these y's isolated, is before you sub that out, you might want to go with y squared minus 6y plus 9 and rewrite that. Otherwise, you're going to have to sub that in and then subtract 3 and then square it. I mean, it's kind of up to you, but I think that this is the easiest way to see it. If you wanted to do that before you even made this substitution, it does not matter the order in which you do that. Oh, and you know what? I should just say, remember when you're taking a product to a power, you kind of like distribute the power to each factor. So we'll write this as r squared cosine squared theta. And then y squared is r sine theta squared minus 6r sine theta. And then since you're going to be subtracting 9 from both sides, if you want to take 9 off both sides now, that's fine. And you can just say that that's set equal to 0. We're going to go through and do the same thing with this term that we did over here. So we'll say this is r squared cos squared theta plus r squared sine squared theta minus 6r sine theta is equal to 0. And now we're going to employ a familiar trick that we've used a bunch of times before. Sine squared theta plus cosine squared theta equals 1. So if you would like to factor out the r squared first, if you find that to be most beneficial for you looking at this, that's fine. So you'll have r squared times, and then you've got this factored piece. I guess you can do whatever you want to do with this side. We might as well just let it be right now, leave it right here. Minus 6r sine theta equals 0. And then I'm already regretting that. R squared minus 6r sine theta equals 0. That's fine. Actually, this is fine the way that it is. Since we want to try to solve this for r, if you want to factor out the r again, you can. And remember that zero factor property that says that if you have these factors set equal to 0, either r must be 0 or r minus 6 sine theta equals 0. You can divide that r out on both sides, and then this leaves you with r minus 6 sine theta equals 0, and then r equals 6 sine theta. All right, in your calculator, it's going to be really easy to see how this graph kind of plays out. And since you know something about the graph of sine theta, we can really make a connection between what you know about the graph of sine theta and this polar graph. But also, before you even learned anything about that, you learned about these types of equations in algebra. Now, if this is not screaming out at you, I'm going to remind you what this is. This is actually a circle. Oops, circle. Remember that the equation for a circle is x minus h squared plus y minus k squared equals r squared. In our case, h would be 0 because we're not taking anything away from the x. So the center coordinate would be 0 and then 3, because remember, k is whatever follows the minus sign. So this would be a circle, and in our case, the center would be 0, 3. And our radius would be 3 because we have r squared equals 9. So that's what our graph looks like. So we can graph this pretty easily. The center's at 0, 3. The radius is 3, so I know that I'm going to go out 3 units in every direction. It doesn't have to be perfect, but you just basically need to have this on the right axis. We're going to do this in reverse in a few minutes too. I think it's a little bit easier in reverse. But this is what you're looking at. Now remember though, your calculator won't actually graph this equation because this equation is not a function. So when you're in function mode, you would actually have to solve for y in this case and do a lot of completing the, you have to, not completing the square, sorry, you'd have to use the square root property to solve for y, and then you'd have to do 2 different equations, one with a plus and one with a minus. This is something that you did in algebra if you wanted to graph that. So you'd have to get y equals, and then you'd have plus a radical, and then a negative value of the radical. The nice thing about polar coordinates is that your calculator will graph a full circle for you if you are in polar mode. So we know what the circle is supposed to look like based on what we know about algebra. But now if we go to our r equals menu, we can see that we're going to be able to generate this exact same graph by using the equation r equals 6 sine theta. Man, I was totally going to do this lecture earlier, and there was all this sunlight outside, and I was just like, yes, I got to do this before the sunlight goes. Just could not get it done. So here we are. It's twilight. Heavenly shades of night are falling. It's twilight time. Don't tell me that you're too young to know that song, because I'm like 50 years too young to know that song. It's called Twilight Time. You should look it up. I think it's the Platters, I want to say. Anytime it's twilight time, I think of that song. All right, r equals 6 sine theta. So go ahead and 6 sine theta. We're going to see what we get here. Now, remember, I changed your bound for theta. So I'm really interested to see what happens here. Let's switch back from 0 to 2 pi. Because it's polar, we usually like to kind of go from 0 to 2 pi. Before you do this, however, before you look at the graph, you might want to think about what could actually be happening here. Notice that this graph is going to go from 0 to pi over 2, and then back down. It's going to hit these points from 0 to pi. So you're not really going to be expecting a whole lot other than negative r values as you get underneath this axis. So I'm going to keep mine from 0 to 2 pi, and then let's graph it and see what happens. Graphs it twice for the exact reason that I just said that it would. Go back to maybe just pi. I'll graph it one time. And remember, I could only see that because I had the little like magnifying glass thing selected, or whatever you want to call it. The reason this graphs itself out in 0 to pi is because I only am covering values on this graph from 0 to pi. Once I get to values that are greater than pi, the only r values I'm going to get over here are going to be negative. They're going to be heading back the other direction. And I know that the whole idea of polar graphs and coordinates is very new to you still. But so if you feel like, how would I have known that? You don't know that. This is just me sort of planting the seeds and just building this for you as we go through. And hopefully, as you keep seeing more examples, you'll start to kind of figure out how this works. But you're kind of graphing your way up, and we're going to graph these in slow-mo, by the way, in 9.5. You're starting at 0, and then as the angle gets bigger, your radius is increasing up to here, and then the angle keeps getting larger, and the radius keeps getting larger up until it's going to get as large as it's going to get. And at this point, your radius is 6. And that makes sense because this angle is pi over 2. The sine of pi over 2 is 1. The radius in that case would be 6 times 1, which is 6. As you start to increase that angle towards pi, you can start to see that the radius is going to decrease. The distance between the origin and any point on this circle is now getting smaller and smaller as you work your way down. And eventually, I mean, if you think about this with radial lines, there's a value r for an angle. There's another one. I'm just drawing random ones. But these are all just angles theta that work their way through, and the radius gets larger up until it gets to 6. And then at that point, these radial lines get smaller and smaller and smaller as you work your way down. And then once you get to pi, the radius is 0, as you would expect. So if you go past pi, your radius values will become negative because we know that sine is negative in quadrants 3 and 4. So hopefully we're getting kind of, you know, some good base knowledge here. Awesome. Let's work the other direction. This will be example 4. Convert the equation from polar to rectangular form in Sketch. I'm still drinking my coffee, and it's like 4:20 p.m. That's how late I slept today because Thanksgiving just like completely took it out of me, guys. Oh. So many side dishes that I ate, you know. My stuffing was amazing though. All right, the first one I want to graph, very, very basic, is r equals 3. Now, we do have to convert this, but remember that we do have a formula that says x squared plus y squared is r squared. So if we have this equation, and I know that r is 3, well then if I wanted to convert this to rectangular form, I would just say that r equals 3 is this equation. X squared plus y squared is 3 squared, which is 9. And this we know is a circle with center 0, 0, and radius 3. Well, this is actually probably going to be one of the easiest things in the world to graph. When r equals 3, what that means is you're just looking at the radius always being 3 all the time, no matter what the angle is. So the angle could be anything in this world, does not matter. Radius is 3 all the time. And that does match up with this graph, with this equation, center 0, 0, radius of 3. Same idea. So I know this is almost so subtle that you're like, what's the difference even? This is the graph that represents both of these equations. R equals 3 is just a circle of radius 3. And then, of course, you already have this equation for a circle from algebra. This one's easier. So if you're always thinking like, oh my gosh, polar coordinates are so hard, I don't know what's happening. Well, think about it in terms of circles. This is technically much easier than that. So polar equations are not always going to be so crazy and difficult. It's just what you're not it's just not what you're used to at this point. But this is what the graph would look like, depending on, you know, how you wanted to think about that. So R equals 3 is just going to be a circle. How about R equals 2 cosine theta? Okay, so we're sort of going to be like going backwards the other direction from what we did in example 3B. This time, we're just going to be working with a cosine function. Now, you are looking for R equals, or I'm sorry, you're looking for x equals R cosine theta. Now, if I'm going to convert this to rectangular form, that means I want to take the r's and the thetas and I want to turn them into x's and y's. Right now, I really, really, really want an r cosine theta so I can make this an x, but I don't have it. It's okay. We're going to force one. I know anytime we force things, you're like, can she do that? Yes, she can do that. I'm going to multiply by an r on both sides of the equation. I'm going to force it to be there. Now, remember that r cosine theta is x. So I have now r squared equals 2x. And then you're wondering, okay, fine, but now we still have an r squared. What is she going to do about that? Well, remember that r squared is x squared plus y squared. We're going to make that substitution. X squared plus y squared is 2x. Okay, now technically you've converted this. However, you want to convert this to something that actually means something to you algebraically. So something that you're familiar with from algebra. So what we're going to do is what we've done so many times in this class. We're going to complete the square. I don't know what it is about completing the square that I love so much. I don't know, you guys. There might be something wrong with me. I'm not really sure. X squared minus 2x plus y squared equals 0. I just want to get all the variables on one side, and then any constants I'm going to move to the other side when I'm done completing the square. So I'm going to turn this into a perfect square trinomial. In order to do that, I need to find half of the middle term's coefficient squared. So half of 2 is 1, square it, and I get 1. Now, I don't need to complete the square on y because I don't have any like linear y terms. I just have y squared. But what I do to one side of the equation, I have to do to the other. So now I can say I have x minus 1 quantity squared plus y squared equals 1. And now, all of a sudden, before you even realized it was happening, you're seeing that you have this equation for a circle. This is a circle with center at 1, 0, and the radius is 1. Right, x minus h squared plus y minus k squared. And by the way, if you're wondering, like, well, how do I know it's a circle and not an ellipse? Remember, we kind of talked about this last week, but first of all, it's a circle because there's a plus sign. Second of all, there's a 1 on the right-hand side. Well, maybe that's not necessarily the case, but it would be an ellipse if you maybe were dividing by a different number in each one of these terms, or if one of these terms had a coefficient on it. For a circle, you're always just going to get the variables squared plus the variables squared equals some number. That'll be your circle. You won't really, I don't even think you're going to be seeing ellipses in here, even when we talk about area. So I guess I was just sort of bringing this back to algebra, bringing it back to something you're really familiar with. Okay. All right, so we can graph this, and then if you would like, you can check this in your calculator. Oh, you know, we should, because I wanted to kind of bring this back to those bounds we were talking about from changing your window values. So this is a circle with center at 1, 0, and the radius is 1. So here's your center. Your radius goes out to 1. I know mine looks like an ellipse, but it's not. It's actually a circle. So let's see what happens when we graph this. Like for instance, what would happen if I only went from 0 to pi over 2? Let's see. Let's see, you guys. It's like getting crazy dark in here. I know you can't tell, but it's like pitch black in here. So hold on a second. Turn on my trusty lamp. There we go. Okay. And then so my neighbors don't all get to see the amazingness that is me doing an asynchronous lecture. All right. So our graph is cosine theta. So what I was saying was, let's see what happens if we only graph this from 0 to pi over 2. So when we do that, by the way, think about what's going to happen. I'm going to start out looking at what's happening at 0, and I'm going to work my way through all the way up, and these angles are going to get larger and larger and larger, and we're going to see that eventually that radius is going to go back down to 0, because the radius starts out being as large as it's going to get at 0, because the cosine of 0 is 1. In this case, our radius would be 2 there. Cosine of 0 is 1, so the radius would be 2, which it is. And then as we work our way through from 0 to pi over 2, you're going to see this radius decrease. And you're going to see that we're not going to get this full circle. And we'll talk about what we have to do to get it. A couple different things we could do. All right, so 2 cosine theta. There it is, 2 cosine theta. I want to change my window, mostly just for demonstrative purposes, from 0 to pi over 2. So I'm going to take my angle up to pi over 2, and I want to show you what happens. Graph. Only the top of a circle. Oh, and by the way, it looks like an oval or the top of an ellipse just because that's the way that your calculator is set up. The screen happens to be wider than it is tall. It really is circular. You can always adjust that in your zoom settings. You can change it to zoom square. I think it still works zoom square in, yeah. Then it'll look more like a circle. You can even zoom in and see this a little bit better. Okay. So I hit zoom 5 for zoom square, and then I hit zoom 2 to zoom in. So you can see that this is just the top half of the circle. Well, that's what we were expecting to happen. Now, we could do a couple things to get the bottom half of this circle to generate. We could take this all the way from 0 to 2 pi, because as we work our way over here, even though we don't have anything graphed in quadrant 2, as long as we're looking at angles that are over here in quadrant 2, we'll get negative radius values that will still generate parts of our circle over here. So watch what happens if you switch your window instead of stopping at pi over 2 to go to pi. There it is. So you might be thinking like, well, wait, how did that happen? Because there wasn't anything graphed over here. So going to pi, yeah. Doesn't matter, because all of those values just showed up as negative r's that moved the opposite direction. So you can pick an angle value over here in quadrant 2, and the r value will show up over here in quadrant 4. I mean, think about it. Cosine is negative in quadrant 2. So if you were to think about something like the cosine of 3 pi over 4, well, you'd have 2 times root 2 over 2, which is the square root of 2, but it'd be negative. So your radius value would be down here, because it would be 3 pi over 4, but in the opposite direction. See that? Another thing you could have done, thinking about all the possibilities here, go back to your window. We could have drawn this from negative pi over 2 to pi over 2, and we still would have been able to generate that graph one time. Sorry, I meant to say negative. So if we started this at theta equals negative pi over 2, that's not pi. We're pi over 2. And then we took this up to positive pi over 2, and then we graphed it. You'll also get that whole graph to generate. So you can really play around with these values. Watch what happens if we went from 0 to 2 pi. What do you think is going to happen? 2 pi. What? Whoops. You guys, I hit the wrong button. Yikes. Okay, what was our graph? 2 cosine theta. I got a little carried away here. Okay, so 2 cosine theta. I'm just going to take my window from 0 to 2 pi. Oh, that's what happened. I was like in the middle of that. Okay, watch. Are you watching? Here we go. Graph. 1, 2. Graph your circle twice. Do you know why? Because it graphed it once from 0 to pi and included all those values down here. But then when it got over here to quadrant 3 and it started picking angles, it again started graphing negative values up here in quadrant 1. So it started to regraph this part starting from here, kind of worked its way around like that. So, and when it got over here to quadrant 4, it just regraphed this bottom part with positive values of cosine. Really interesting stuff, you guys. I highly recommend just kind of playing around with those. Let's do another one. So like I said, 2B was kind of like, 3B was like 2B in reverse. So for 2B, we started out with the rectangular equation that was a circle that was just translated up, and then we switched it over to polar. And then, no, that was 3. Sorry, I said example 2. Example 3B was like example 4B in reverse. So for 4B, we started out with polar and then completed the square and turned it over to 2 rectangular. And again, it was just a circle that was switched over. But hopefully now, let's kind of talk about the similarities between those. For example 3B, we had r equals 6 sine theta, and you could see that the circle was actually just shifted up from the origin. Whereas example 4B, we had 2 cosine theta, and when it was a cosine theta, it was shifted to the right instead of up. This is general behavior that you can expect to see every time. So when it's just r equals and then a cosine theta, you're going to be shifted over left or right. If it's a sine theta, it's going to go up or down. So very interesting stuff, guys, just kind of making connections between these rectangular and polar graphs. What else was I going to do here? Yeah. One thing that you won't see a lot, but I didn't want to not talk about it, is something like this. Theta equals 7/6 pi. This doesn't have an r in it, but what I asked you to do was not just graph this, but also to convert to rectangular form. If it's in rectangular form, you don't want r's and thetas, you want x's and y's. The way that you're going to convert this over, remember, is we had tangent theta equals y over x. So you can use that here to switch this back to rectangular form. All right, so we're going to go with tangent theta equals y over x. So tangent 7 pi over 6 equals y over x. And then think about your tangent values here. 7 pi over 6 is like right here. Just a little bit over pi. And the reference angle is pi over 6. It's just pi plus pi over 6. 6 pi over 6 plus pi over 6 is 7 pi over 6. So you're in quadrant 3. Tangent is positive in quadrant 3. And then you're just looking for the tangent value for that reference angle. And that would be root 3 over 3. If you want to write that as 1 over root 3, that's fine. And by the way, if you're not sure, you could always take the sine over the cosine. So you know that the sine of pi over 6 is a half. The cosine of pi over 6 is root 3 over 2. And when you take the sine over the cosine, it's 1 over root 3. Or you can write that as root 3 over 3 if that's the way that you learned it way back when. So I want to write this in one more line, actually. So the tangent of 7 pi over 6 is the square root of 3 over 3. You can write that as being y over x. And then, since we're going to want to graph this, you'll want a y equals. So you can just multiply both sides by x, and you'll get y equals the square root of 3 over 3 times x. And I know this looks a little different just because it's got an irrational number in it with the square root of 3, but this just, y equals mx, and then b is 0. So if you were going to graph this, it would just be y equals 3 over 3 x. What is root 3 over 3? 1 divided by the square root of 3 is about 0.577-ish. Okay, so that's going to be your slope. So the y-intercept is 0, and then you're going to go up about half and then over 1. So that's 1, that's 1. You're going to go up a little more than a half and over 1. Graph that line. And then if you're like, wait, how does this relate to what we were just talking about? Blah, 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 I don't get it. Well, that's how it relates, because this is 7 pi over 6. So it's just making this angle in each case with this particular slope. So that's how. How would you graph this in calculators? Well, unfortunately, you're not going to be able to graph this one because you don't have an r equals, but you can graph this one in your calculator. You know how to do that, so I'm not going to go back into function mode. But if you see something where it's just theta equals, then you're just talking about this line that goes through the origin with whatever theta is as the slope. So you won't see it a lot, like I said, but just wanted to make sure to show it to you in case it pops up. What else did I want to do? Oh yeah, something, I know this one's kind of weird. Trying to figure out how exactly I had it written 3 different ways. Which way do I want to show it to you? And I was like, oh, I'll just make a game time decision. Okay, I'm going to write it like this. R sine theta equals 3. Okay, so you know that we're trying to, if we're trying to convert this over to rectangular form, that we want to get rid of all of the, actually now I'm regretting writing it like this. Sorry, guys. Oh, wish I hadn't done that, but that's okay. All right, I will show you the other ways that I had it written, because I think it's good to see the different ways in which this might be presented to you. Okay, r sine theta equals 3. Now, it might be your first impulse to solve for y and then convert. So you might want to go, okay, fine, r equals 3 over the sine of theta. And then you might even say, okay, fine, r equals 3 cosecant theta. These are all equivalent ways of saying the same thing. This is what I was talking about. Which way do I want to show it to them? And then I picked that one. But you might see it in any of these forms. And I just want you to get familiar with just kind of seeing the way this could be presented. If you see it in this form, I know it is your urge to have r by itself, and then you wouldn't know what to do. However, what we always like to have is r sine theta, because we know y is r sine theta. This is just y equals 3. So even though these forms are solved for r and they seem like the best, most wonderful thing, remember that when you're talking about converting, we're really just trying to get specific expressions that we can substitute. And r sine theta happens to be a big one for us. So if you have something like that, or if you can generate something like that, don't think like, okay, well, I have this already, I'm good to go. You want that to be in a form that you can use. R sine theta equals y. All right, so this is y equals 3, and you know that y equals 3 is just a horizontal line going through 3. Now, this one's really hard to visualize when you're thinking about this in polar form, because you're like, wait a second, but like as we work our way through here, it's hard to generate this. It is, but think about what happens at 0. The sign of 0 is 0. You can't divide by 0. What that means is like you can't actually get any R values off this. They're parallel, and you're not going to be able to generate this graph. However, as soon as R starts to increase, and remember this, this graph goes all the way out. Even for really small values, eventually you're going to hit that. So this value of R is going to be really long, and then it's going to get shorter as you work your way through. So here, the sign values, as you increase from 0 to pi over 2, are really, really small. So you're dividing by really, really small values, and you're getting a really, really large value for R. But as you work your way up through these angles, heading up towards pi over 2, well, the sign of pi over 2 is 1. So that would just be 3 divided by 1, which is 3, which is why you get this radius here of 3. It's so hard to think about radiuses and how they relate to straight lines. I really want you guys to be able to visualize this, though. So as your angle theta increases, the radius values are actually getting shorter and shorter and shorter and shorter, up until they get to their shortest possible value, which will be right here. And then again, you're going to start to increase these values again. And then as your angle goes up towards pi, the radius values will continue to increase because this line has to keep getting longer and longer and longer and longer until it gets infinitely long. And then you get to a point where you're parallel and you'll never be able to touch the line. If you wanted to graph this in your calculator, I would recommend doing 3 divided by sine theta. You don't have a button for that. It might exist in your catalog, but go with 3 over sine theta to graph in calculator. I feel like we've done enough of those, so I'm going to let that one be. But you know how to graph the rectangular form. What else did I want to show you here? R equals 4 divided by 2 cosine theta minus sine theta. This is very similar to another one that we did first. This is going to be sort of like example 3a, but in reverse. Go back, look at that. Ringing a bell for me. So look at what we had for example 3a when we were done. So we originally started out with this rectangular graph, and then we got over here to this polar form, which we said like, wow, that really doesn't look much like anything we know about, but we did know about it. So we're going to work this one in reverse, switching it back to rectangular form. Okay, so think about what you're looking for. You're looking for x equals r cosine theta, y equals r sine theta. So what you'll want to do here is cross multiply. And then distribute. So you'll have 2r cosine theta minus r sine theta equals 4. And now that you're here, you're like, oh, got it. Good. R cosine theta is x. R sine theta is y. No big deal. This is technically fine for the conversion unless you're specifically asked to give the equation in slope-intercept form. I tend to say if you can solve for y or if you can solve for r, depending on which way you're heading, you should do that. So y is going to be 2x minus 4 And then we can just go ahead and graph that. 1, 2, 3, 4. So y is 2x minus 4. The slope is up 2, right 1. Up 2, right 1. Got a y-intercept of -4. And then your line looks like this. 2, right 1. Oh, you know what? I moved over too many. I went right 2, not right 1. Sorry. I'm looking at this kind of sideways, but I don't know why I did that. Up 2, right 1 is here. Your slope is 2. Not 1. Okay. So your line looks kind of like that. And it's a little bit harder to do a little mental math on looking at what happens to your angle theta to graph this. I mean, you can always put it in your calculator. We showed this with example 3a, but this one is definitely much easier to see in rectangular form. What did I want to do? Oh, I just wanted to do one more complete the square one. I don't know. I just feel like it's helpful to see it. I just really want to solidify the completing of the square just so that you guys feel really confident in it. 10 cosine theta plus 24 sine theta. Okay, so we did this for, what was the example? R equals 2 cosine theta. So we did this a few examples ago for just 2 cosine theta, but in that case, we didn't have the 24 sine theta. But that's okay. We're gonna make it happen now. We're gonna convert all of this over so that we have it. Wonderful. Okay, multiply every term by r. We've used this technique before. Remember, we're just trying to create a situation where we can use r squared equals x squared plus y squared, and a situation where we can use x equals r cosine theta, y equals r sine theta. You're going to get familiar with these because you're going to see these types of equations over and over again. So you'll have a good sense for what to do when you see them. So we have x squared plus y squared equals 10x plus 24y, just subbing all that out. Now, this is a classic example of a place where you're going to need to complete the square. So go ahead and move everything to one side. If you want to do this in one step instead of two, that's fine. Does not matter to me, but I'm going to do mine in 2 steps here where I'm going to just move everything and then complete the square. So I'm going to create some perfect square trinomials. Half of 10 is 5, square it and you get 25. Half of 24 is 12, square it and you get 144. What you add to one side, you must add to both sides. Now you can complete the square, factor. And this is 169. So this is going to be a circle with center at 5, 12, and the radius is going to be 13. I don't really feel like we need to graph this. I think we've done enough of this that I feel we've sufficiently covered it. If you'd like to graph it, feel free, but I think at this point we're pretty comfortable with being able to graph circles. Okay. So that was what I had to say about 9.4. I want to talk about 9.5. I'm going to talk a little bit more about graphing these equations. Let's start this fresh page. So 9.5, like I said, it's kind of a hodgepodge, and they give you all these topics and then they don't have a lot of exercises to choose from. And like I said, the reason there aren't a lot of exercises is because the math starts to get really complicated. So they can only present these very basic examples and show you how to do it. And it's very hard to come up with examples that are within the realm of what we know how to do as far as integration is concerned in calc. It does have some examples for using computer algebra systems. We don't have a math lab available to us right now in our class, so I'm not even going to force you guys to use Maple to use a computer algebra system. So I just want to sort of get your feet wet with some of this stuff, so you've seen it and you're familiar with it, but it's not anything we're really doing an extensive deep dive into in 9.5. But what I do really want to dive deep into is this first example where we're going to be just graphing these polar equations. And this is just really going to go along with what we have already been doing in 9.4 with just some of the informal graphing. This time I'm going to be super formal about it. And I really want to show you how these graphs are generated. I think it'll really kind of put everything together. Okay, so this section is officially called Polar Equations. Parametric equations of polar equations. Don't get scared about that. It's no big deal. And arc length of polar equations. A lot of times, this initial part with this first example for polar equations is just given to you in a section where you're learning about polar equations, which we just did in 9.4, and then the calculus is kind of split up into another section. So I kind of find it odd the way this was organized, but I'm sure the authors have their reasoning. I would like to direct you, if you have a book, you don't have to open this up, but I think it's really helpful to just kind of to look at these graphs on page 715. I'm going to put mine up here for you. There's a little chart, and it just sort of gives you a rundown of the different types of graphs you're going to see. I'm going to go through graphing one of these with you and one of these, well, more like one of those actually. But in this class, in this particular section, I might actually assign you some graphing work to do by hand, just because one of you told me, and at first I thought it was so odd, but then I saw it for myself and was like, yes, this is happening. But the multiple choice graphs in Achieve don't always display properly. Apparently the multiple choice graphs in Achieve sometimes just give you descriptions. Now, I believe the descriptions are actually just the alt text for any student that has disabilities. So like any sort of visual impairment, you would have like an accessibility thing turned on so that you could hover your mouse over something and it would read to you a description of the graph. So you can now sympathize with how a blind person tries to learn math, because you're trying to pick graphs out of a multiple choice, and sometimes on Achieve, all you get is a description. It'll be like, a curve is decreasing from here to there and increasing from here to here, and I don't think it's helpful. So you're going to be graphing stuff like this, these three and those. I'm not going to have you graph any of these, but definitely these three in the top row, and then the rows petals, I'm going to have you graph by hand. And actually, you know what? I'm going to assign some graphing by hand, because on your test, when we go through your material for chapter 9, I'm going to have one question on there where I'm going to say, draw out a table of values and graph this polar curve. Now, technically, I can't force you to not use your calculator and at least just eyeball the graph. It's kind of like if you took my Calc 1 class with curve sketching, I kind of tried to make it as best as we could, but it's hard to do online. But I'm going to actually have you fill out a table of values and just sort of at least show me the progression of how you were able to graph this curve. Oh, whoops. Okay. Yikes. So I am going to put up some graphing homework by hand for you to do these, because I think it's most instructive versus trying to read the Achieve the Achieve descriptions and pick the right graph. I'm like, I don't want to do that. I find it confusing. So why would you want to do that? Nobody does. So if they don't load properly, that's a problem. And I can tell because when I preview them, they're graphs, they're actual graphs. But then when I open them up fully, it's like they don't load properly. Ugh. Okay, not going to get on the achieve tangent again. But anyway, these are the types of things we're going to be looking at. And this chart is really nice because it kind of helps to show you what you can expect to see. Now, these are looking very, very similar to the circles that we drew. The big difference is with the circles, we didn't have this plus or minus component. We just had a cosine theta or a sine theta. And we talked about how that just took a circle and it shifted it either left, right, or up or down. In this case, we're going to be adding a term to that. Now, depending on the signs that are involved and the coefficients, you might get three very different pictures. So even though these equations look like they're the exact same, it all depends on the actual coefficients that are involved. Depending on what those numbers are, your graphs could look, pretty different, not like totally different, but they could look different. And we're going to be looking at a lot of these types of graphs in 9.6 when we're talking about area. We'll put like two of these on a coordinate axis together. We'll talk about where their intersection points are, and then talk about finding the area between the curves and like finding the area inside the inner circle, or like finding the area inside the inner circle and between the y-axis, finding the area of the piece that's between the x-axis and the top of the graph. Oh, it's going to be fun. I don't know. I really like 9.6. I think it's my favorite of all the sections in chapter 9, just because it's like really interesting to see how you can isolate these pieces. And it's just one of those things that's very rewarding when you're done with it. When you're done with it, you're just like, wow, it worked out and that was really cool. And you feel good about it. We all want to feel good about our math work, right? All right. So example 1, let's see, graph the polar curve. And I'm only going to do 2 of these with you because there are so many different variations. I can't do like 15 examples. But once you do 1 or 2, I think you start to really get the hang of it. Apparently I can't properly write today. Graph the polar curve. Maybe I need to finish this coffee a little bit faster. Okay. So you're going to do 2 things here. One of them is graph the polar curve, and the other one is going to be I want to write the exact instructions actually that you're going to have. Find parametric equations that represent the polar equation. Gosh, you guys, I was just about to give you like a trigger warning that there's going to be a lot of trig involved, and then I realized like, oh my gosh, trigger, it's like a trig warning. There's a trig warning. I feel like calc students need this. We're going to be doing a lot of trig. This is your trig warning. It's going to be a lot of it. So if you can't handle it, you might want to stop the video and go look at your unit circle for a while and come back, because we're going to be doing a lot of trig, being very triggy with it right now. Okay. A triggy warning. R equals 3 minus 2 sine theta. You know what always happens when I have to record these async lectures? I'm just like, oh, I don't want to do this. Oh, I hate doing this. But once I get into the math, it's so fun that I'm just like, oh, this is great. This is like a total mood booster. I wish that that was the case for you. Do you feel like when you watch the lectures, you're like, oh, this is really feeling happy right now? Okay, sorry. Now I'm totally going off on tangents here. All right, let's see. We've got 3 minus 2 sine theta. Now, we started to graph these in the last section, and you got a really good idea by looking at your window in your calculator and changing changing your theta min and theta max, you got a really good idea of what you could expect by looking at your, what you would expect to see when looking at this graph. Now, there's nothing I can do to stop you from graphing this in your graphing calculator and getting a good idea of what you need to expect when you graph. However, I'm going to ask you to make a table of values, and it's going to be a long table, not like the longest table you've ever seen, but we're going to include lots of different angles here because we want to get a really good picture. And the thing is, if you don't include a lot of different values of theta, you're not going to get a good picture, and you're going to miss some of the key important things that are happening in your graph. So it's really important that we hit all the special angles. So all the time you spent in trig learning those special trig function values, really going to come in handy now. I'm going to make a table of values, and I'm going to start with, you know what, you might even decide that you wanted to do this vertically. I'm going to make mine horizontal, but I'm going to pick values of theta. And we're just graphing these by hand. Graph the polar curve by hand. I'm going to ask you to do this on your test for one problem, where I'm going to ask you for a table of values, and you're going to have to give me all the values and graph this by hand. So, and I'll even have the polar graphing grid on your test for you. It'll look kind of like a bullseye because I want your graph to look good. Okay, so that's going to be given to you on your test, and you're going to fill it out and graph your graph with the table of values. Okay, so we're going to have theta and we're going to have r. Now, I don't really see the sense in starting at negative values of theta. If I were you, I would start at 0. Leave yourself a little space because your r values might be a little larger. We'll have to see what happens. But I would take this up to pi over 6, and then I would go up to pi over 4, and then pi over 3. And you're going to work your way up to pi over 2. And then you're going to keep going. You're going to go up to, let's see what comes next. I got to think about this now. 2 pi over 3. Okay, so if you're looking at your unit circle, you might even find this to be easier. So I'm picking up pi over 6, pi over 4, pi over 3, pi over 2. Here's your 2/3 pi. This is 3/4 pi. And this will be 5 over 6 pi. And then you'll get up to pi. I told you this would have a lot of values then. Okay. Then you're going to go up another pi over 6 to 7 pi over 6. Then we're going to go up to the special angle, which is 5 pi over 4. And then to the next special angle, which is 4/3 pi. Then that puts you up to 3 pi over 2, 5/3 pi, 7 pi over 4, and 11 pi over 6. Once you get to 2 pi, you should be back where you started. And I know this sounds really excessive. If I want specific values on your test, I'm going to just give you a really huge table, and then you can fill the whole thing out. I'll ask you for those specific values. But I'm going to ask for exact values, and you might find that to be annoying, since if you're going to graph this, the exact values aren't going to be very helpful. You're going to actually need decimal values. But I want to know what the exact values of r are, and then you'll graph this using some approximate values on your grid. Okay, so some of these are going to be easier if you want to fill them out first. Like, for instance, the sine of 0 is 0. 2 sine 0 is still 0, and r is going to be 3. Now, what we're doing here is we're really just going to be building our graph from 0 all the way up to 2 pi. We'll see what happens. It's kind of up to you if you want to build it as you go or wait till the end. Personally, I just like to fill out the whole table and then make my graph, but that's up to you. The sine of pi over 6 is a half. Multiply that by 2 and you get to 1. 3 minus 1 is 2. Okay, some of these are going to be a little trickier when they have radicals in them, the sine of pi over 4 is the square root of 2 over 2. If you want to work here, you can. I'm just going to maybe put this on the bottom of the one I'm working on. 3 minus twice, and then the sine of pi over 4 is the square root of 2 over 2. So the exact value will be 3 minus the square root of 2. For pi over 3, the sine of pi over 3 is root 3 over 2. So the sine, oh, I already said that. Sine pi over 3 is root 3 over 2. The 2's will cancel, and you'll get 3 minus the square root of 3. I'm going to put some approximates down here in a few minutes. The sine of pi over 2 is 1. 2 times 1 is 2. 3 minus 2 is 1. You're seeing that these values are continuing to decrease. For 2 pi over 3, very similar. Remember that sine is positive in quadrant 2. So when you're looking at 2/3 pi, you're actually going to end up getting the same value that you got for pi over 3 because that value of the sine will be the same. So you can say that this is, again, 3 minus the square root of 3. For 3 pi over 4, same thing. Sine is positive in quadrant 2. So sine has the same values at 3 pi over 4 and pi over 4. So I have 3 minus the square root of 2. For 5 pi over 6, again, same value as pi over 6. It's in quadrant 2. The sign is still positive, so you can say that's happening at 2. Now the sign of pi is 0. So the sign of 0 is 0. 3 minus 0 is 3. And you're sort of back to where you started. Now you're going to see these values change as you work your way down into quadrants 3 and 4. Because in quadrants 3 and 4, the sign value is negative. So you're going to be doing minus and negative. So what you're going to see is these radius values are actually going to get a little bit larger. Because with minus and negative, you're going to be just getting bigger values down here. So for 7 pi over 6, the sign of 7 pi over 6 is actually going to be negative 1/2. The sign is negative in quadrant 3. So you'll have, instead of 3 minus 1, you'll have 3 plus 1, which is 4. At 5 pi over 4, you're going to have 3 minus twice and then negative root 2 over 2. So you'll have 3 plus root 2. Same idea here. Instead of having 3 minus the square root of 3, you're going to have 3 minus twice negative root 3 over 2. So you'll have 3 plus the square root of 3. The sign of 3 pi over 2 is negative 1. So 3 minus 2 times negative 1 is 3 plus 2, which is 5. So this is the largest value so far that we've seen for the radius. So 5 pi over 3 is going to have the same value as 4 pi over 3 because the sign value is the same. And then at 7 pi over 4, you're going to have the same value as 5 pi over 4 because, again, the sign value is the same. 11 pi over 6 will have the same sign value as 7 pi over 6. And at 2 pi, again, you're going to get 3 because the sign of 2 pi is, once again, 0. All right, so let's get a couple of these decimal approximations that we need. One of them is 3 minus the square root of 2, which is approximately 1.59. 3 minus the square root of 3 is like 1.27. 1.27, 1.59, and then we need 3 plus the square root of 2, which is 4.4-ish. 3 plus the square root of 3 is about 4.7. Three plus the square root of 2. And we now have some approximations. We don't have to approximate too closely because we're going to have to just graph this. and we can only graph so close with these decimal approximations. Okay, so let's see here. I'm gonna make this big and huge because I want to be able to see all these little fine points. The largest value I have for R is 5. So I need to take this out to R equals 5 concentric circles. So 1, 2, 3, 4, 5, be something like that. I'm going to attempt to make these look like circles. All right, so this will be the circle for radius 5. And this is just our graph grid. So you might want to make this a little bit light. You know, it always ends up looking footballish, right? Because this is not actually part of your graph. It's just the grid. So you don't want to get this confused with what is actually happening on your graph. If it looks like a football, you know, you do the best you can, you guys. How many years have I been drawing circles and mine always still look like footballs? Some of us are just going to be a lost cause. Some of you will be drawing beautiful circles. I've even had students come into class with compasses, and they use them to draw the most beautiful circles. Whoops. I just want you to be able to graph, that's all. There we go. Okay. Now, what you might also want to do, since you have a bunch of angles already, is graph them. So you have about a 45-degree angle here. Do the best you can. That's pi over 4. Do the same thing over here. That's 3 pi over 4. 5 pi over 4. 7 pi over 4. Now, pi over 6 and pi over 3 are not halfway in between. They're a little bit closer to pi over 4. Do the best you can. I mean, in the end, it's all just, you know, you getting a good approximation. But, you know, that's about a third of the way to pi. Do the best you can. So that will be 2/3 pi. This one will be 5/6 pi. And then do the same thing down here. So this one will be 7/6. This one will be approximately 4 pi over 3. 5 pi over 3. 11 pi over 6. Something like that. All right. Now, the magic starts. I'm way too excited about this. When theta equals 0, r equals 3. Here's where we're really going to be just getting down into the nitty-gritty graphing these. We've been doing everything in our calculator. Now we're doing it by hand. When theta equals 0, r equals 1, 2, 3. Right there. This point is on our graph. If you want to graph all the poles first, that's fine too. You can do that. But I'm just going to go up from 0 to pi over 2. When theta is pi over 6, r is 2. So pi over 6, 2. And, you know, you do the best you can. If your graph is kind of footballish, then this is going to get graphed a little bit funny. I'm already seeing how that's going to affect the shape of my graph. So I'm going to try to fix that a little bit. Do the best we can. At pi over 4, we're at approximately 1.59. So at pi over 4, we're about 1 and then a little bit more than a half. Maybe right there. At pi over 3, we're at approximately 1.27. So on this radial line, about 1 and then a little bit, maybe around the corner mark. Now, if you start to see that all of a sudden you have a point that's like way up here, you might be like, wait a second, that doesn't look right. Something must be wrong. These should form a nice symmetric shape. So just, you know, kind of be thinking about that as you work your way through. At pi over 2, r is 1. Okay, now we should be seeing similar behavior on the other side. At 2 pi over 3, we have 1.27, a little bit over a quarter. Then we're up to 1.59 again. Then we're up to 2. And at pi, once again, we're over here at 3. You know, yours on your test will look nicer because you'll have actual like polar coordinate grid. Okay, now we're going to work our way down on the other quadrants. At 7 pi over 6, the radius is 4. So 1, 2, 3, 4. Down there. Now, as long as you're seeing the same thing on the other side, that's all that matters. At 5 pi over 4, we are looking at about 4.4, and then we'll be at 4.7 and 5. So 4.4-ish, 4.7-ish, and 5. And notice that you're going to see the same thing heading in the other direction. You're going to go 4.7, 4.4, 4, 3. So 4.7, 4.4, 4, and then back to 3. Now you're going to connect these with a nice smooth series of curves. And hopefully you did like a decent enough job. Mine looks like it could definitely be better, but we can do the best we can. You're going to see this shape start to appear. We can always adjust it later if need be. It looks like this. It could be the distance of my angles here. It could just be where I put the points, but not too bad. Now, if you'd like to compare this with the chart that you see on page 15, 715, not page 15, certainly weren't doing this on page 15. Let's see, we have 3 minus 2 sine theta. The 3, I'm trying to include everything in here. Three minus 2 sine theta. A would be 3, B would be 2. So A is greater than B, and we can't use this one because in this case the coefficients are the same. In our case, they're not the same. But our A is 3, our B is 2. Our A is greater than B, so we're looking at the second situation that we have here. We would have a loop if you had A being smaller than B, which we don't have in our case. But we have this one. If you'd like, you can always graph it on your calculator just to check, make sure that you have something that looks the same. And then we'll also look at the table here because I think it's helpful to see the table in your graphing calculator, even though I want you guys to be using exact values. I still think it's a good thing to look at. One day I'm going to find like an optimal view for this, and then it'll be like, whoops, don't need it anymore. Okay, 3 minus 2 sine theta. Did I enter a 0? No. Okay, I don't know what I did. 3 minus 2 sine theta. I think our window is already 0 to 2 pi. It is. Notice that if you only go to 0 to pi, it's only going to graph the top half. And I think the nice thing is now that we've done all this, you can see why. If you only look at values of theta from 0 to pi, you're only going to get the top half. So we're going to use 0 to 2 pi. We're going to get this entire graph. I'm zoomed in right now, so I'm not going to get the whole thing because remember I had that zoomed in. But if I go back to zoom standard, there's your little circle. It shows it graph once, and then we'll square it out again. And we can zoom in a little bit, but if we zoom in all the way, we'll miss that. So you can always adjust your window so that your X min value, we're not really going out that far. And you can go from -5 to 5. Well, not 2, 5. And then your y-min can be -5. Your y-max can be 5. You'll get a little bit of a better picture. And now it's not square anymore because I set x and y min and max to be the same. But yeah, this is what we graphed. This is what it looks like. This is totally fine. For your test, this is what I'm going to expect to see. So I'm going to have a table of values set up for you, probably. Otherwise, I'll just tell you to make your own using all the special angles. And then you graph this picture. I'm going to have you do some of these by hand for your homework. Oh, you know what? I forgot one piece of the directions, which it's not a big deal, but Achieve is going to ask for it. So I want to make sure you're ready for it. There's a part of the instructions that says to find parametric equations that represent the polar equation. All you have to do there is for the parametric equations, x equals r cosine theta, x equals r is 3 minus 2 sine theta, cosine theta. So just substitute r for r. And whether you simplify that or not, I don't know if it's going to make a difference on Achieve, but r sine theta. So if you want to distribute the cosine and then distribute the sine, fine, whatever. But these are the parametric equations that represent the polar equations. So technically, you could graph this also in parametric mode using those two equations. Okay. So I feel like a lot just happened here, and then it all just kind of wrapped up. I want to show you another one of these special types of curves that I said I would do another example for. So I'm going to do one more example in this graphing by hand portion. This will be B. I might have to call it quits after this for today. What do I have to do after this? I mean, technically, all the stuff that comes after this kind of goes with 9-6 anyway, so it's not really the end of the world if we just do this graphing by hand. We did a lot with graphing today, and I do feel like it's a totally new concept, so I want you guys to have some time to let it sink in. I'm not too upset about that. Okay, that's fine. Let's talk about then B being the graph. R equals 4 cosine 5 theta. I want to dig into this one a little bit now that I know it's going to be my last example for the day. Because I really want to talk about this because we're going to be looking at stuff like this when it comes to looking at area of like petals of graphs for polar equations. So I think it's really important for us to be able to isolate a petal of the graph. And if you're just like, petal, what's she talking about? Well, I just so happen to be talking about this. Now, you only have equations for 3 and 4, but as long as you have an odd value here on your theta, you're going to have just a petal with an odd number of, or I'm sorry, a rose with an odd number of petals to it. So this is a rose curve. How it's listed, yeah, it's just a rose. But ours is going to have 5 petals because we're looking at cosine 5 theta. So kind of want to focus first on talking about the tips of the petals, just because these aren't exactly special angles. So this is a rose, and again, this is on page 715. It's going to have 5 petals, and that's because we have 5 theta. That's going to dictate that for you, and you can always put this in your graphing calculator just to verify what's happening. But you're going to need to know in 9-6 how to determine the angles for which you have these petal tips. So I kind of want to focus on that. We will be graphing this by hand. If you want to get an idea, though, for what you're going to be looking at, go ahead and graph it. 4 cosine 5 theta. 4 cosine 5 theta. And maybe we'll go back to a standard zoom. Oh, it's beautiful. And notice that it graphed twice. Did you guys see that? If you had your little bubble thing on, you would have seen it actually circled over twice. Which way is the best way to see this? Okay. If you take your window from 0 to regular old pi, because mine's on 2 pi, look at the regular old pi and then graph it again. It'll graph 1 time. So, all right, so that's good. So that means that we only need to go from 0 to pi. That's the way these rows graphs are going to work, actually. All these rows are going to graph from 0 to pi. That's not going to be the case with the last example where you're going to need 2 pi, which we just did. But the roses will only need pi. And you can, like I said, verify that using your graphing calculator. All right, now you can see from the picture on the graphing calculator that one of those petals goes all the way out, and that's at theta equals 0. So what I'm going to ask you to find first is the petal tips, because like I said, those are not going to come out with your special angles. So the petal tips are going to happen when R is the greatest value that it can possibly be. Because remember, you want to go all the way out as far as you can in order to get that petal tip. And that's going to be the largest R you can find. Get largest values possible for R. All right, so the way we're going to do that is, well, I know that, for instance, R is going to be as great as it possibly can be when cosine is as great as it possibly can be. Cosine can be at most 1. That means that your petal tips are going to be at most 4, because I'm going to have 4 times, and we're going to figure out when cosine is going to be 1. So the petals, maybe I should say the petal tips, will be 4 long. That's for the radius value. So I know it's going to go out to 4. And you can also see that on the graph that we have here. You can actually see this petal tip goes out to 1, 2, 3, 4, which makes sense. So we want cosine to be as large as it possibly can be. Cosine can never be greater than 1. And then when you multiply that by 4, your radius value can never be greater than 4 times 1, which is 4. So we're going to figure out where that's going to happen. So cosine will be 1 or negative 1 when theta is equal to 0, pi, 2 pi, 3 pi, 4 pi, so on and so forth. Any sort of integer multiple of pi is going to give you a cosine value of 1 or negative 1. I mean, think about what you know about your unit circle. Here and here, the x values will be either 1 or negative 1. So that happens at 0, pi, 2 pi, 3 pi, 4 pi, so on and so forth. Technically, you can include 5 pi. You might not need it. So we don't really care if it's 1 or negative 1. I know we said we were looking for the largest possible value for R, but we really are thinking about this in terms of absolute values, because, I mean, whether R is positive or negative, it's going to look the same on the graph. It's just, it might be going into the graph instead of out onto that radial line. So what I need to do is set my angle 5 theta equal to 0 pi, 2 pi, 3 pi, 4 pi, 5 pi. The reason being is I'm going to be taking the cosine of 5 pi, which means I want to be looking at cosine 0, cosine pi, cosine 2 pi, so on and so forth. So I want to make sure that the cosine of my angle is going to be equal to these values. Now, if that's the case, then I know that theta can be 0. We saw this on the graph. When theta was equal to 0, we had a value of r that was 4. But I also have theta equals pi over 5. When theta is pi over 5, we are going to get a pedal tip. Now, it should be in the negative direction, but we should be able to see that on our graph. I know it's kind of hard to visualize pi over 5. It's a little bit more than pi over 4, and it goes in the opposite direction. So probably this one down here. But that's going to be one of your pedal tips. And actually, if you would like, you can even watch this regraph itself. You might have to switch you might have to say something, even if it doesn't switch, to get the circle to come back. Oh, it's not doing it. What it's actually going to do, though, when it shows you how it's graphing, it goes whoop, 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 and it kind of goes around that way. So where it starts is here at 0, and then it kind of goes and swings back around this way. So that's the first, or that would be the second pedal tip that it hits. Then it's going to come up to this one, and it's going to go down to that one, up here, and back down again. And when we graph it, you'll see that. All right, so theta is 2 pi over 5, theta is 3 pi over 5, theta is 4 pi over 5, and theta is 5 pi over 5, which is pi. Okay, now the reason we did this is because this is going to tell us where the pedal tips are located. If you don't have the pedal tips, then your graph is not really going to be complete. You're going to end up just getting a bunch of weird values in between, and you'll be like, okay, fine, and you'll cut it off too soon because you won't realize it's a pedal tip. So it's really important that we isolate these. Now, let's say that you, instead of having cosine 5 pi, you had sine 5 pi. Well, if that was the case, then you would want the sine function to be equal to 0, and the sine, or I'm sorry, you would want the sine function to be 1. So you would set this equal to 0 because sine 0 is 0, not 1. But you would definitely use, in that case, I'm going to even write a note, if it was r equals 4 sine 5 theta, you would find pedal tips by letting 5 theta be any value where the sine will give you 1, so or negative 1. So you'd have 5 theta is pi over 2, 3 pi over 2, 5 pi over 2, so on and so forth. So this is just like a side note, but that would be how you would find the pedal tips if it was sine instead of cosine, by looking at the greatest value they could possibly be. And for sine, that would happen. You would get sine theta equals 1 at pi over 2, or negative 1 at 3 pi over 2, positive 1 at 5 pi over 2, negative 1 at 7 pi over 2, positive 1 at 9 pi over 2. And then you would solve for theta for each one and get those values. Okay, so now that we have the pedal tips, I want to go through and make a little chart. Now, the nice thing here is we know that we don't need to get every single angle from 0 to 2 pi. I only need to focus on angles from 0 to pi because that's going to graph the whole thing for me. Now, technically, it's kind of a cheat because I only knew that because I looked at my calculator. But now you know that for the future, that for a rose curve, it's going to graph in pi, not 2 pi. So you don't need to include as many values. So we're going to get some thetas and some r's. So we'll start at 0. Now, if you want to put these in your chart, you can, but you don't have to. You can sort of see where they're going to be. I don't know. It's up to you. I'm not going to put them in my chart. I'm just going to, when I do my graph, I'm going to account for them in there. I just want to do these the same way each time, so I don't want to throw any curveballs at you. Pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. And then we'll see what happens. This is actually a really fun one to graph. I know what I think is fun is a little bit convoluted maybe, but that's fine. I'm trying to transfer some of this love to you, this math love. All right, when r is 0, I'm going to rewrite our function here because it's so far away. 4 cosine 5 theta. When theta equals 0, 5 times 0 is 0. The cosine of 0 is 1. R equals 4. Well, we already knew that because we already said that when theta equals 0, 5 theta is 0. That was a pedal tip. So we know that this is also going to be a pedal tip. At pi over 6, we're looking for the cosine of 5 pi over 6 or cosine 5 pi over 6. Well, 5 pi over 6 is in quadrant 2. Cosine's negative in quadrant 2. So you're looking at negative root 3 over 2. So this value is actually going to be negative 2 root 3. Oh man, I should have given you some more space here. I guess I should have given me more space. Okay, at pi over 4, we're looking at, oh my, you guys, I'm going to have to go real crazy with this. Should have left some space. Okay, you know what I'm going to do? Actually, I'm going to organize this a little bit better. I'm just going to say r of pi over 4. I'm just going to do my work down here. Is 4 times the cosine of 5 pi over 4. We'll do that. Now, 5 pi over 4 is in quadrant 3. Cosine's negative in quadrant 3. The reference angle is pi over 4. So you're going to have 4 times negative root 2 over 2, which is going to be negative 2 root 2. Now, at pi over 3, we'll do r of pi over 3 is 4 times the cosine of 5 pi over 3. Now, 5 pi over 3 is actually, I know we had this drawn out here, but we have 5 pi over 3 in quadrant 4. So that's good. Cosine's positive in quadrant 4. And then our reference angle is pi over 3, and the cosine of pi over 3 is a half. So this will be 2. And you might be thinking like, what's happening here? Don't worry, you'll see it on the graph. At pi over 2, we have 4 times the cosine of 5 pi over 2. Remember that 5 pi over 2 is coterminal. If you take off 2 pi over 2, you'll be left with 3 pi over 2. That's taking off a pi. Sorry, take off 2 pi. Take off 4 pi over 2, and that just leaves you with pi over 2. It's coterminal with pi over 2. So this is just 2.5 pi. And then this value for the cosine is 0. Now at 2/3 pi, you'll have 4 times the cosine of 10 pi over 3. And now find the coterminal angle. So take off 2 pi, which is 6 pi over 3, and you'll have 4 pi over 3. This is in quadrant 2. Cosine's negative in quadrant 2. The reference angle would be pi over 3. The cosine of pi over 3 is a half. So this value will be negative 2. All right, 3 pi over 4 So that'll be 15 pi over 4. Take off 8 pi over 4, which is pi over 2. And you'll get 7 pi over 4. This is an angle in quadrant 4. Cosine's positive in quadrant 4. The reference angle is pi over 4. The trig value is root 2 over 2. So this will be 2 root 2. At 5 pi over 6 is the cosine of 25 pi over 6. I forgot the 4. All right, so 25 pi over 6, take off 2 pi, which is 12 pi over 6, and it brings you to 13 pi over 6. Take away another 12 pi over 6, and you just get the pi over 6. And that brings you back to quadrant 1 again. So you're taking off 4 pi in this case, which is 24 pi over 6. And that gets you here. So cosine pi over 6 in quadrant 1 is positive. 4 times root 3 over 2 is going to be 2 root 3. And that gets us back to pi. R of pi is 4 times the cosine of 5 pi. The cosine of 5 pi, remember, you're looking for a coterminal angle. Take off 2 pi, that gets you to 3 pi. Take off another 2 pi, that gets you to pi. And that gets you to negative 4. All right. Let's see what kind of craziness we get here when we graph this one. I'm just looking at my crazy notes. Okay. I'm going to put this on the next page. Hopefully you have your chart handy because I'm not really going to be able to see mine all that well. Let me graph this. And then we'll do this one and we'll be done for today. We're going up to, let's see, our pedal tips are at most 4. So we only need to go up to 4. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. My scale is not great. You know, this always happens every time. It's not an alarm telling me to wrap up, just in case you're wondering. Okay. We'll do the best we can. It's very footballish. Maybe some of you guys really like football and this appeals to you. I'm not huge into football. Not really into football at all. Not even lightly into football. All right. I have pedal tips that I want to mark out here. I can also mark out, though, my special angles. This one is pi over 4. You don't even have to label them if you don't want to, especially in quadrant 1. If you feel like, okay, fine, I got this. I know what they are. I'm going to put my quadrant 2 labels on. Just so that they're there. This will be 5 pi over 4. This one will be 7 pi over 6. And this one will be 4/3 pi. Uh, 5/3 pi. 7/4 pi. And 11 pi over 6. Should you feel so inclined, you can go ahead and put your pedal tips on. You might want to do that. It's kind of up to you. You're going to have to eyeball where they're located. If you want to put them on now, and then you can sort of match up the rest of the graph with them, you might find that it helps you graph. I don't know. You pick the order in which you either want to put the pedal tips on first and then graph your other points later. Up to you. Either way, this point's on here, so we had to get there at some point. But we might just want to put the tips on just so that we can kind of see where they are. All right, so we have a pedal tip at pi over 5. However, note that at pi over 5, this gives us a negative pedal tip because the cosine, if we're talking about 5 pi over 5, it's the cosine of pi, which gets you -4. And it's also going to be negative. So here's r equals 4, r equals -4, r equals 4. So like, for instance, 4 pi over 5, you're talking about the cosine of 4 pi, which is 1. And then 4 times 1 is 4. So you can kind of see how they go from negative to positive. So positive, negative, positive, negative, positive. Okay, so we already drew the pedal tip at r equals, at theta equals 0. Now we can draw it at pi over 5. Our tip is going to be -4. Now, if you're not sure where pi over 5 is, that's fine, not a big deal. If this is pi over 4, this is pi over 6, pi over 5 is going to be smack in between them. So if you're in between these two, then you're in between these two, and you're going to have a pedal tip right there. This one I'm going to label is going to be r theta, so -4 pi over 5. Whoops, that's your pedal tip. You have another pedal tip at 2/5 pi. Your radius is going to be 4. So 2 pi over 2/5 pi is 40% of the way to pi. You're thinking about this as maybe being, okay, pi over 3 is 1/3 of the way to pi. Pi over 2 is a half of the way to pi. So 40% of the way to pi is somewhere in here. So you might want to say that this is 5th pi. So it's going to be between 1/3 and 1/2. So that's 40% of the way. So like 0.33, like 0.5. It's going to be a little bit closer to pi over 3, but you're somewhere around here. 40% of the way to pi. We will label it there. And then you'll have a radius of 4. So you can say that you have a tip, and maybe I'll turn this into an ordered pair. Your radius is 4, and you're at 2/5 pi. That's going to be another pedal tip. You have another pedal tip at 3/5 pi, and your radius will be -4. So 3/5 pi, 3/5 is 0.6. So this gets you to about 2/3 is 0.67. So this is approximately where 3/5 pi would be. It's going to be the other direction from here. So take it pi over this way, and it's going to be approximately right here when you take it negative. So this point is going to be r, which is -4, and then 3/5 pi. Not to be confused with pi over 3. We haven't graphed anything there yet. But your 3/5 pi is going to come down to be a negative radius. And you should start to see that these pedal tips begin to look equidistant. Now at 4/5 pi, your radius is 4. 4/5 pi is about 80% of the way to pi. 3/4 is 75% of the way to pi. 5/6 is like 0.83. So 80% is about somewhere in there. It doesn't have to be perfect. Do the best you can. And the radius is positive. So I would say that this point is another tip, and it's located at 4 and 4/5 pi. And again, though, now you're seeing that you've got 5 tips of 5 pedal tips, and they look like they're about equidistant. So you should have them all, you know, somewhat equidistant, depending on how you drew your unit circle, distributed like that. Now, we'll start to graph this using our table of values, and we'll be able to really use our pedal tips to complete the graph. So we already have this point at 0,4. At pi over 6, we have -2√3. Negative 2 times the square root of 3 is approximately negative 3.46. Negative 3.46. And negative 2 root 2, might as well get that while I'm in here, is about negative 2.82. So I'll just put that in here, negative 2.82-ish. Whoops, sorry, you can't see that. So 3.46, 2.82, and we'll use those values again. So this will be positive 2.82 and positive 3.46. And let's see if we can complete our graph here. See if we can get this picture. I'm trying to show you everything. Okay, so at pi over 6, we have about negative 3.46. So going the opposite direction. So here's our pi over 6. And then we're going about negative 1, 2, 3, and a little under a half. But I want you to see what actually is happening with this graph. You know, we might want to, you could come up with all the center points too. But what's happening is we started here, and then our graph sort of swung through and went this way. Now, if you don't believe me, we're going to have to just get these 0 values. So if you would like, it would probably be extremely helpful to do. Find where the graph hits the origin. And that's going to happen when cosine 5, well, this is going to happen when r equals 0, happens when r equals 0. So when r is 0, the graph's not going anywhere. And r equals 0 happens when the cosine of 5 theta equals 0. Now, the cosine of 5 theta is going to be equal to 0 when 5 theta pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and 9 pi over 2. So if you're not sure what's happening in between this point and there's a big leap to get over here, get some values here where r is 0, and you can verify that that's what's happening with the graph. So we would say here that theta would be equal to pi over 10. 10's in the denominator. And theta is equal to 3 pi over 10. Theta would have to be equal to, in this case, pi over 2, because the 5s are going to cancel out. 7 pi over 10. And 9 pi over 10. Now, you won't be able to see these on your graph because they're all going to be at the same point. All of them are going to have a radius of 0, so they're all going to be sitting here at the origin. But it kind of allows you to see what's happening in between your values. So you went from 0 to pi over 6. No, you went from 0 to, oh yeah, this would be your next point, pi over 10. And then pi over 6, and then pi over 5. So you would kind of have to draw these all in order. But you can see that at pi over 10, you've got this really small angle here. As you start to increase your way up, you do indeed go through the origin because you have a point at 0 and pi over 10. So your graph is going to sort of go like this. You're going to start to see these petals start to emerge. Let's see what happens next then. All right, so we graphed this point. Now at pi over 4, we're at negative 2.82. So at pi over 4, we'll be at negative 12.82. Gets us to right about there. We'll see how good of a job we did. Go through that point. And then what happens is the next value that we get to will probably be, let's see, pi over 3, 3 pi over 10. So this is 0.33 pi, and this is 0.3. So you actually get to, let's see, 3/10, 0.3, 0.33. Yeah, you hit this first at the origin. And then when you're at 0.33 pi, you get up to 2. So it happens very fast that you work your way up to 2 here. And then you go up to 0. Or I'm sorry, at pi over 2, you would end up at 0. So you have to hit your tip first because this. You guys, I was in the middle of my lecture. My internet went out and I don't know where it happened. And then I muted myself because my kids came in here and started talking to me. And then I was just on camera being muted. I don't know where I left off now because I don't know where this thing cut me off. I'm going to have to splice it later. But I was somewhere on here making this graph. So what I'm going to do is I'm going to finish up this sketch. And you've already seen what has happened because you've seen it in your graphing calculator. But I'm actually going to post, I'm going to go through and make a full chart where you can see all of the points being done in order here. Because I think it's really helpful when you combine this all into one chart. It's just that I didn't really think about doing that until after the fact. And now I'm running out of time. So I think I'm already past the 2-hour mark. So I'm going to finish up this sketch and then I'm just going to make you a nice chart, but you can kind of see now how the values work their way through. If you have questions, I mean, feel free to bring your questions to the office hour on Monday. Yeah, Monday I'll see you. But I mean, obviously this is a little bit of an exaggerated pedal that I didn't quite get through here. But this is the way that the rose curve works. You can see how we use a bunch of different ideas to find both pedal tips and then to talk about our angles at which our graph would be hitting the origin to really get a complete picture here. And if you'd like, you can even, increase this up to values all the way up to 2 pi if you wanted to just create more values on your graph. You could do that. But you don't have to. This graphs itself from 0 to pi. But being able to combine this with the tips of the pedal and the origin values is really helpful. So anyway, but I think I'll put this all in one chart, like I said, and post it for you so that it's available so you can kind of compare this to what you're seeing graphically in the video and just kind of really see how this thing is graphed, because it is really an abstract idea when you think about like, okay, well, I'm here and now all of a sudden I'm up there, but that's okay. That's where I'm supposed to be. And then just the fact that this is going to swing around the way it does. Anyway, next time, because I only had like 3 more examples to do in this whole session, actually, just because, like I said, there's a lot to do, but there's not. Next time we'll talk about how to find intersection points because we're going to need those in order to talk about the area between polar curves. And then we'll just talk a little bit about finding equations for tangent lines, which is super straightforward. You saw that for parametric equations. And then we'll talk about area. So I don't think I'll get all that done Wednesday, but at least in the async lecture, I'm going to get as much done as I can Wednesday because you have your test a week after that, and I don't want you to be learning too much of the rest of this asynchronously. So we'll do as much as we can on Wednesday. All right. Got a little crazy here at the end. You guys enjoy and email me if you have questions, and I'm going to assign, like I said, some homework by hand so that you'll have that. Okay. Right, wonderful. I'll see you next time. That is all.